All right. So what we're looking at is finishing up the notes and finishing up exponentials. So let's talk. We were talking about the difference between compound interest and continuously compounding interest. We want to remember for continuously compounding, the thing that makes it continuously compounding, if we look at that, we know that the limit, the end behavior, if we're looking at the end behavior of n as it's approaching infinity, that means the number of times you are compounding, that is of the compound interest formula. In other words, this becomes this as the limit of n, the number of times you compound, goes to infinity. So that becomes P naught e to the RT. Okay? We know what E is. We know E is a natural base rate of growth. And that's for anything that's continually growing. You'll notice if you look on your calculator, you will see on your calculator the ln button, e to the x is above that. And so if you do second ln, you get e, and if you do e to the first power, it's approximately 2.718. And what's really funny is in early math, pi is like king of the irrational numbers. Everything pi. But really, as you get into upper level mathematics, like you guys are getting into now, e is a much more important naturally occurring number than pi is. E is the thing, okay? If we have a lot of different things have a continually growing exponential growth, and so any that's continuous can be modeled with this E. In other words, that natural base. In other words, we get typically y equals ae to the kt, okay? So that's a natural thing. E is that natural fit for this exponential continuous growth process. So let's look at the check your understandings. You guys were supposed to have kind of looked at this, but we're going to look at this together. If you look at number 1, estimates of the number in millions, and anytime you're doing one like this, you ought to put down, oh yeah, hey, in millions, of U.S. households with digital televisions given by, and look, we have an exponential function. How do we know it's exponential? Because look where the variable is. It's in the exponent spot. T represents years after 2000. It says, part A says, is the number of households with digital televisions increasing or decreasing between 2003 and 2007? Well, we look at this and ask ourselves, is this a growth equation? Well, we know that if it's going to be growth, if you think about it, if it's going to be growth, then you know B is greater than 1. Well, what is B in this case? Well, B is 1.012, and that is indeed greater than 1. So it is, and remember we call this the constant ratio. So yes, it is growing. It's we want to make sure we actually answer with the language they're asking us. They asked us to say, is it increasing or decreasing? The justify, if you look at it, the justify part right here is this, because B is greater than 1, and that's the constant ratio. The actual answer that we give increasing or decreasing is the yes, it's increasing part, okay? So make sure when you answer these questions that you're answering what they're actually asking you. It says, what does the 30.92 represent? Well, the 30.92, if you remember, the 30.92, that's going to be your a sub 0, isn't it? So that's going to be the starting amount and that's going to be in millions of U.S. households. And this is where we just write what they say. U.S. households with, and notice I'm just literally taking U.S. in millions of U.S. household digital televisions. Well, if this is starting, since we're talking about after, this would be in the year 2000. We need to specify when, okay? So now, what does the 1.012 represent? 1.012 represents the constant growth rate. Okay? In other words, number of TVs grows by what? 1.2% each year. Okay? So you can't just say it represents the constant growth rate. You have to tell them that you really understand that this is the part because it's 1 point something, it's increasing. So it's a growth. And then take this 0.012 and know that it's 1.2%. All right? So now look at part C. Use the model to estimate the number of U.S. households with digital televisions in 2015. Okay. So this is telling us we have to look at T. T is going to be 15. So then we're just going to plug in. And we're going to say D is equal to 30.92. 1.012 raised to the 15th power. And this becomes a calculator problem. Okay? So this becomes about 36.9783, and so that would be 36.9783 million households. Okay? Now, part 2. On the day of a child's birth, you're going to deposit $25,000 in a trust fund that pays 8.75% interest. So we want to know that on the child's 25th birthday, weekly versus monthly and continuous. So let's start with weekly. So weekly, if they're born, we know, first thing we know is that T, let's put over here, T is equal to 25, right? A naught is going to be equal to 25,000, okay? And interest rate R is going to be 0.0875. All of those things are things we're going to need to know. So now if we're talking about weekly, we are looking at our, and if you think about it, we're looking at compound interest. So P naught, 1 plus R over N to the NT. So really we probably should have called that P naught instead of A naught. So let's call this P naught. So we're going to do P naught, which is 25,000. Times 1 plus R, 0.0875. Weekly, there are 52 weeks in a year. Raised to the RT, so that's 0.08. RT, NT, hold on. NT, excuse me. N would be 52, so this becomes 52. Times what? 25 years? So what does that become? If you throw that through your calculator, $222,413.32. That's pretty good. Monthly is going to be that same deal, only this time it's going to be 25,000 times 1 plus 0.0875. Monthly is going to be divided by 12 this time, so then we'll have 12 times 25. Shouldn't be as high, should it? So this one's going to be $221,000. So not a huge difference, but different. And then continuously we're going to be changing formulas, and we're going to be changing the formula to the P naught e to the RT. Okay? So P naught is going to be that 25,000 times e to the 0.0875 times 25. And we'll figure out that is going to be about $222,822.57. All right. So now, number 3, number of bacteria, certain population is going to increase. Now it is continuous. We're giving us a rate per hour. They're giving us a P naught, aren't they? Number of bacteria after T hours. Well, this is going to be P naught e to the RT, isn't it? So what is P naught going to be? 1800 at ground zero at T equals 0. E, the rate, is going to be 0.081 times T. So there is our growth. Now it says find the number of bacteria in the population after 6 hours. Okay, so then it just becomes P of 6, 1800, e to the 0.081 times 6. Gives us 2,926.44 bacteria. All right, so in every one of these, if we're talking exponential growth model, that continuous model, you're looking for your P naught, you're looking for your R, okay? And that's really it, and T. But these are the things that you'll plug into the formula, and this is what you'll use as you evaluate it, a piece at a time. Okay, so now let's look at the last chunk of exponentials. How often should you take Dayquil to construct an exponential model? So we're going to look at cold medication. Vicks Dayquil often includes chemical dextromethorphan, which is a cough suppressant, okay? You can get them over the counter. They're low risk. You can get side effects if you take too much of them. All right, so now we're looking at this thing called a half-life of 3 hours. That means every 3 hours your body cuts the amount that's in there in half. You've heard this in terms of radiation before. Half-life of an isotope. Those of you who've been in chemistry or currently in chemistry or AP Chem, half-life is a big thing there. Radiation levels, the radiation level cuts in half every certain amount of time. Different isotopes have different half-lives. Same thing with drugs. And this becomes a big deal with things like dextromethorphan. We need to know what those are. How long is it till it's completely out of your system, or effectively completely out of your system? All right, so it says in a 30 milliliter dosage of liquid Dayquil, there's 20 milligrams of dextromethorphan, and after 3 hours, 10 milligrams would still be in your system. How many milligrams after 6 hours, after 9 hours? Well, think about it. 6 hours is going to be effectively two 3-hour chunks. So we're going to go from 20 milligrams to 10 milligrams, and from 10 milligrams to 5 milligrams. In other words, we've got 2 of these 3-hour chunks, okay? Now, after 9 hours, that would be a third one. So 9 hours is going to be 3 of those 3-hour periods, okay? So we're going to go from 20 to 10 to 5, and then to 2.5 milligrams, okay? So we're looking at this not from the standpoint of what's happening, but every time we're doing this, effectively, what are we doing? We are dividing by 2. Dividing by 2. Or you can think of it as multiplying by 0.5 times 0.5 times 0.5. Okay? Same deal, aren't they? So it's going to go down and down. It says how many milligrams of the drug after 10 hours? Well, for 10 hours, we really need to know how many of these 3-hour units do we have. So we're going to take 10 and divide it by 3. We get 3 1/3 of these 3-hour units. Okay? So how do we do this? Well, let's think about this in terms, the easiest way to do this would be to construct what we call a model. Well, what's our growth rate? Well, it's a decrease, isn't it? So this shows we have a decrease whose rate is 0.5. So can we construct this? Absolutely we can. We know that the rate of going down is going to be, we're starting with 20, right? We know it's being reduced by 50%, so 0.5. And it's going to be raised to what? Well, how many units of this? How many times does this happen? 3 1/3. So if we do that, what we get is 1.98 milligrams. Now, can we do a formula for this in your system after t hours? Sure we can. We know d of t is going to be equal to the base amount, which was 20, the amount, the growth rate, or in this case, the decay rate, which is 0.5, and we're going to take the number of hours and divide it by what? Well, hours is what? Hours is time, t for time, right? Because we're doing t, so be careful with that. Well, we can't just say hours because it's 3-hour increments, so we have to divide by that t by 3. Because that's basically what we did each time, wasn't it? So now it says what percent of the drug remains in your body after 1 hour. Okay, well, d of 1, we're going to use this. 20, 0.5, 1 divided by 3. Throw that through your calculator, and you get what? Did we really need to do this? Here's my question for you. Did I need this piece of it? Guess what? I'm going to get rid of that. Why? Because we're not really finding the amount of drug left. It's asking the percent of the drug. It's a different question, guys. The percent of the drug would be 50% every 3 hours. So we're going to do 0.5 raised to the 1/3 power, which would be 0.7937. So 79.4% remains, which means what? 100 minus the 79.4 would be what? 21.6% lost. Okay, we're eliminated. So now it says write in an alternate formula in the form of AB to the T that can be used to amount the model amount of dextromorphin in your system after T hours. Okay, so D of T, we know we're starting with 20. Now, this is not that, this is the percent left in your system, right? So what percentage is left? In other words, we've taken 50% for every 3 hours, and now we've just turned it effectively. Do you realize that's what we've done? We've taken 50% every 3 hours and changed it to 79.37% every 1 hour, which means now we can do it by hour. So instead of putting 0.5 here, we're going to get rid of that, to say it's not 0.5 because that's 0.5 every 3 hours. We're going to use the 0.7937, okay, every t hours. And so let me just write it in terms of t rather than having to say t divided by 3. Okay, are they different? No, they're the same end result. Think about it, okay? This is equivalent to 0.5 times t divided by 3. These things are the same, okay? Think about it. This would be the same right here, if you think exponent rules, would be the same as saying 20 times 0.5 to the 1/3 power, right, raised to the t power. And that's exponent rules. And this right here is that 0.7937. If you didn't understand what we were talking about, that's what that represents. So that's how this guy became that guy. So now, it says customers are instructed to use the medicine as directed. For adults and children 12 years and over, 30 milliliters every 4 hours. And it says, okay, using the recommended, and then you take your first 30 milliliters at 8 a.m. Using the recommended dose, calculate how many milligrams of dextromethorphan will be in your system at various times throughout the day. Okay, well, how do we figure this out? I want you to think about it. If at 8 a.m. you took your first 30 milliliters, you have, 20 milligrams in your system at 8 a.m. So now how much do I have the next time and the next time and the next time? Well, this is 2 hours, isn't it? So we're going to do literally that 20.7937 to the second, which gives us 12.60 milligrams. And then 8 a.m. to 12 p.m. What is that going to be? So see, this is 4 hours, isn't it? So here's where the tricky thing is. It's having you take a dose every 4 hours. So the first thing we have to figure out right here is how much of the original dose is left after 4 hours. If we look at that, we see it is 7.94 milligrams, but then they're having us take another dose, in which case we know there's another 20 milligrams in our system, so that ends up being 27.94 milligrams. So now we're at 27.94 milligrams at noon. Now, from noon to 2 p.m., again, we have 2 hours. So now instead of 20 here, we can't do 20. We have to now change this to 27.94 because that's our new baseline now, isn't it? 27.94 times 0.9737 to the second power. And we end up with 17.6 now. So now we're at 17.6 milligrams. But here's that cycle again. So now it's 4 hours again, which means for this guy, we're now looking at the original dosage for the second time, 27.94. We're going to do 0.97937 raised to the fourth power. Which is 11.08. But then we're now, 4 hours have passed, so now we're taking at 20 milligrams again. So we're at 31.08 milligrams. Look what's happening. It's going up, 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 up. Every 4 hours, you're getting a little more, a little more, a little more, a little more, aren't you? So now we're at this. You try this one. Try the 2 hours and then do the 4 hours on your own. So what are you going to get at 2 hours? Just pause the video, do the calculations, and see if you get it right. Hopefully you've done that, and you're going to find that you get 19.58 milligrams here, and then you end up with 12.34 before, and then plus another 20, which ended up giving you 32.34 milligrams after that. This right here is why they tell you not to take more than a certain number of doses in a 24-hour period, because they know it's just going to continue to keep growing and growing and growing in your system, because it doesn't, the first dose doesn't completely go away before you take the second dose. All right? Your science fact for the day. What we're looking at is constructing exponential models. How do we? Okay, so let's look and finish and wrap up here and look at what we've got. So what do we have? Exponential functions. Constructing a model. We know that exponential functions, in our quick notes, models growth patterns, or successive output values over equal input intervals. Are proportional. Providing you're using either an initial value and a ratio. So you're going to use an initial value or a ratio, or two input-output pairs. Why two input-output pairs? Why would those give you the same thing? Remember, if you have two input-output pairs, you have an initial value, and the two outputs can give you your growth rate, can't they? Make sense? Next, we know equivalent forms can reveal different properties of growth rate. Okay, for example, if you have f of t is 2t over 7, that is the same that describes well, this tells me what? A quantity that doubles. How often? Well, let's think about it. How often would be this, wouldn't it? Every 7 years. Whereas f of t equals, remember, we're going to take the 1/7 to the t. That would be 1.104 to the t. Those are the same thing. But this shows growth every year. Okay? In other words, that would be a 1.104 would be 10.4% change each year. So let's look at this, check your understanding, and make sure you know. I'm assuming you're pausing each time to try to answer the question on your own before you check it. You know an element decays by 25% every 5 days. After 10 days, there are 45 grams. You've got to be able to think both directions. How much must there have been on day 0? So we're going to take 10 and divide it by 5 and know that we have 2 cycles. So if we had 2 cycles of 5 days, that means that we started with something, we divided by 2, and we got some amount, divided by 2 again, and we ended up with 45. So if we are going to go the other direction, if you want to think about it that way, going the other direction means we would be multiplying by 2, which would give me 90. And then again, I would multiply by 2, which would give me 180. So we started with what? Oh, wait a minute. 25%, not 50%. Sorry. We're dividing by 4. Is that right? What do you think about it? Decays by 25%. So if it decays by 25%, what are we keeping? Oh, so this is even more wicked. If it were 50%, it'd be easy. So we've got to think about this instead. As if it decays 25%, that means how much is kept? 75% is kept. So we are going to take, let's think about this the right way. We're going to start with some amount, and we're going to say we're going to keep 75% of it. And then what? Multiply by 0.75 again, and we end up with 45. So how do we do this to solve? Well, I want you to think about it this way. We multiplied by 0.75 twice, didn't we? So we started with some amount times 0.75 squared and ended up with 45, didn't we? So some amount x. So how do you solve that for x? Well, we divide both sides by 0.75 squared, divide by 0.75 squared, and we actually end up with x equals what? 80 grams. So you got to think backwards sometimes, guys. Now it says write an equation for E of t, the number of grams remaining of the element after t days. Well, now we know that P naught is 80 grams, right? We know that our R is 0.75 because that's how much we're keeping after t days. Well, it's every 5 days. So think about what we did. E of t, how would we write this before? We just had examples of this. Start with 80, multiply by 0.75, total amount of days divided by 5-day increments. And that's our equation. So let's find E of 7. E of 7 would be 80 times 0.75 to the 7 divided by 5. E of 6 is 80 times 0.75 times 6 divided by 5. And if we're just to do it this way, we'll just do it as division. We know that goes away, that goes away. So what are we left with? Well, this gives me 0.75 to the 1/5 raised to the 7th power, 0.75 to the 1/5 raised to the 6th power. So guess what that gives me? 0.75 to the 1/5. Which is 0.9441. Basically, if you think exponent rules, remember if you're dividing, you subtract. So that would be 7 minus 6 would be 1. So basically, this would be to the 1st power. Okay? Now, Great British Baking Store show. Take their cake out of 180 degrees Celsius oven. Put them in a fridge whose temperature is set at 3 degrees Celsius. After 10 minutes, it's cooled to 150. Okay, and it says this is how it can be modeled by a, b to the t power plus 3 for some parameters a and b. Well, I want you to think about what that would be. What is c of 0? Well, this would be a b to the 0 plus 3. So this would be b to the 0 would be 1. So this would be a plus 3 would be right here. And what did we say it started with? 180 degrees. So we can set this equal to 180 degrees Celsius. So a plus 3 equals 180 degrees. So a is, subtract 3 from both sides, you get 177 degrees. Now, let's look at C of, well, what? C of what? This is time in minutes. So they also give us another one after 10 minutes. So C of 10 is going to be equal to what? We know what A is. A is 177 times B raised to the, what, T? So raised to the 10th power plus 3. And they tell us that is equal to 150 degrees Celsius. So now we have 177 b to the 10th equals 147. We can divide both sides by 177. And we get b to the 10th equals 147 divided by 177. Now how do we get rid of the 10th power? Well, we take the 10th root. And so we get b equals what? 0.97958. So if b is 0.97, is it growth or decay? Just a reminder, it's less than 1, so it is decay. In other words, it's cooling off. Of course it is. So now we can use this. We can actually use this to finish our formula. Our formula says we know A was 177. We know B is 0.97958 raised to the t power plus 3. So there's our formula. So now all we have to do is plug 45 into that. This is our t. So now we're just going to find C of 45. Which is approximately, if you do this on your calculator, 72.94 degrees. So, to recap, what are the things we saw here? We were looking at this, and we were looking at all these different pieces, and we're saying, all right, if we want, and we have a growth rate, remember what we said, either equal input intervals, we're going to either get an initial value and a ratio, or we're going to get two input-output pairs. Well, the two input-output pairs are like we just saw in number 2. The initial value and a ratio is like what we saw in number 1. Okay? In problem, check your understanding number 1. All right, guys, these are your notes for today. You need to now do your, the sub has them for you. You need to do your practice problems, please. And we'll go over all of these and check them when I get back. Today is Tuesday, so you will be responsible for having all of this so we can go over it and then start reviewing all of this on Thursday. See you guys then. Bye-bye.